Next up, we have Sam Burden from University of Washington. Unfortunately, so he was the co-organizer last year, but unfortunately he had a new member of his family arrive, and he was unable to make it, so we're glad to have him here this year. Ready?
Yeah, as Max said, fortunate or unfortunate, depending on your perspective, I suppose. I'm thrilled to be back, and thanks so much. Conference has been amazing so far. Thanks, Jerry, for putting on such a great show. All right, so what I'm planning to talk about today, this is going to be a little bit of a departure from the previous two talks, in that this is going to be a little bit more kind of theory analysis focused. But I'm thinking that, you know what, a little bit of differential topology is exactly what you needed to whet your appetite for dinner, right? So before we dive in too deep, I want to acknowledge the contributions of my collaborators. Oh wait, no, so hold on. It's actually, for anybody that looked through the program and was concerned that I'd moved, I haven't. I'm not at Georgia Tech. My collaborator on this project, Sam Coogan, who might have been automatically parsed, his location might have been automatically parsed into the program. He did all the heavy lifting on the analysis side, and then a postdoc that's shared between me and Tom Daniel at UW, Tom Libby, did all of the help on understanding the actual mechanics. Tom Libby's a postdoc, so he needs a job. I encourage anybody and everybody to aggressively recruit him this fall. He'll be on the job market. And just to see how fantastic he is, you can check out his talk tomorrow at noon. So I'd like to start with just a couple of vignettes that set the stage for what got me thinking about this problem of why or when do feed-forward inputs yield stable behaviors. And this really goes back to when I got started in this community in dynamic walking. As an undergraduate, I did an RU in Dan Kotichek's lab, and that exposed me to this wonderful world of Rex, this six-legged robot that does these, at the time 20 years ago, really spectacular, rapid, stable running behaviors. And what's cool, if maybe you've seen this video 100 times, but maybe you haven't seen exactly what drives this thing, it's actually just a feed-forward clocked input that's tracked with PD reference tracking, just classical reference tracking. So there's kind of nothing too smart going on in the control side of this. Noah's sitting here in the front row. I hope that he won't critique that observation. So something smart is going on in the design and the mechanics that we can just feed in this input and get this different behavior. And you can change the parameters of this so-called Bueller clock. It just makes the limbs go slower when they're near the ground and faster to try to recirculate to get back to the ground again. You can tweak the parameters and the thing will still move, and by optimizing them, you can get it to go fast. So that's sort of on the proof of concept on the synthetic side. And then on the natural side, around the same time, I saw this video that got me just so pumped about getting into this field. This is a now pretty classic experiment from Gendrich and Full, 2002, where they put a cannon on the back of a cockroach, if you can kind of make out in the grainy black and white footage. This is recorded on literally Kodak film, I think, in the 2000s. So here they wanted to perturb a running cockroach. They run fast, they're small, and so it's kind of hard to imagine, especially 20 years ago, how you'd track, let alone kick it with some kind of robot arm or something like that. So instead they just let the cockroach carry its own perturbation device and fired off this cannon to perturb it. And the conclusion from this paper, it's been, I think, debated. I think there's been kind of rich discussion around this conclusion, but what they claim is that the stabilization begins faster than neural feedback could have possibly altered the recovery. So faster than any sensory feedback could have come from anything that's ever been measured in an arthropod, something of this scale, insect, and could have done any kind of processing in the basal ganglia, and then done any kind of muscle activation and changed anything about the recovery. So that suggests that there's something feed-forward happening here. But that's on a very small time scale, because then shortly after that we get to the horizon where neural feedback could have played a role, within 15 milliseconds or something like that. And so then when I was in grad school, I was involved in a revised version of this experiment that significantly extended the time horizon over which the animal receives the perturbation. So here the animal's running on a cart. The cart's going to accelerate. You're seeing a plot of the velocity in the bottom. So that in the reference frame of the cart, it's the animal that accelerates. So this is kind of accelerating the animal's world instead of directly accelerating the animal. And then we looked at detailed kinematics of how its limbs moved throughout this whole process. And so here we're seeing a plot of cart acceleration versus time. So this is no longer like a nice localized impulsive kind of perturbation. This is like spread out, extended over time. But it's very large. It has a huge effect on the animal's biomechanics. So whereas pre-perturbation, it's running pretty straight. Its lateral velocity is very small. But just after peak perturbation, its lateral velocity is the same magnitude, is actually a little bit larger than its forward velocity. So this is me like running at full speed and then a sumo wrestler sprinting at full speed perpendicularly and shoving me, and then I try to recover from that. And what we looked at was, do we detect kinematically, we also did some neural recordings, but kinematically, that's what I'm showing here, do we detect any change in the timing or the motion of the limbs? We would take that as evidence of neural feedback, and what we observed here and what we argued in the paper is that we don't see a change for at least like 100 milliseconds. So these things are running approximately 10 hertz, and so that's at least a stride post-perturbation before we see any evidence of neural feedback. And we're not claiming that this is neural feedback, but just that, up until then, we really don't have strong evidence that there is. And so this is kind of pushing that time horizon back. It's not just the fastest that neural feedback could kick in the cockroach. It's actually, it had, 85 milliseconds that neural feedback could have played a role, but it didn't seem to in our experiment. Yeah, Max.
And why does the cart moving change the kinematics?
You're asking whether the cart's motion would change the kinematics? We thought about that, and we kind of did data munging to account for that, and like overlaying or amplifying or accounting for that doesn't change the effect that yeah. Adding or removing that from the data before we compute that statistic doesn't change the result.
And once the perturbation is gone, you're still looking at the relative phase moving forward. So beyond that point, this can still be clear, right? Do I understand? Like the
yeah.
Is over by the second line. The perturbation is over by the second line. Is that correct?
Well, we're marking here like peak and then halfway, or really just maybe above half g. Yeah, cart acceleration to the bottom. I mean, actually, the cart is still continuing to accelerate for a while, but this munging that we do, where we only use data when the limbs are on the cart, and so they're not being directly like influenced in the air by the acceleration, we do that the whole time in that analysis. Okay, so those are my two vignettes, and what I hope to kind of do is just give you a context. Show off things that I worked on before, but give you a little bit of context for the kinds of systems I'm thinking of. We can build robots and we can like literally engineer them so that the only signal, exogenous signal coming in is this feed-forward reference that then there's low-level controllers trying to track. And then in the case of animals, certain experimental circumstances, the evidence suggests that they're relying in large part, in no small part, on feed-forward input. So what I want to spend most of my time talking about is trying to get a conceptual and analytical framework to try to think about this and to try to capture this. Because, wouldn't it be powerful, wouldn't it be wonderful if we could just build systems that exploit their, dynamical phenomenon of locomotion, and we can just press play and they do what we want them to do, rather than having to do a lot of detailed within stride control. So really quickly, one kind of sub-problem I worked on this is actually the gate controller that's making this Minotaur robot bound. I wanted to put in a little advertisement for longtime friends and collaborators, Gavin Keneally, Avid D, and Dan Kodacek, their startup that sells these robots. And what we did really was Avic's key insight, and then I kind of helped with a little bit of on the back end, the analytical machinery. We generalized this classical notion of dynamical averaging that basically says if you have a system that satisfies a bunch of technical properties and it kind of has a nice stable equilibrium, then if you perturb it with just a small periodic forcing, that you can kind of average out the effect of that forcing and get a nice analytical approximation to what the thing does over multiple strides. So like in practice, what's happening in the case of the Minotaur is that we play in these small little feed-forward periodic inputs U, and then they get averaged out over multiple steps to, in this case, a proportional controller on total energy. So Avik cleverly took these things and had one hopper that's stabilized and another one, and then he couples them in clever ways, and that's what makes the Minotaur hop. But kind of underlying that is just playing these carefully designed and feed-forward inputs that we have nice kind of analytical understanding of what their effect is. So this is like a very, very, very specialized, like particular, not many systems can be amenable to this averaging kind of analysis. And so I want a little bit broader framework to think about this. And so what I thought I would do, if I kept on just throwing up a bunch of equations and things like that directly on the slides, I think that I'd put everybody to sleep, including myself. So I'm going to take a little page from Russ Tedrake's playbook here, and I'm going to switch over and see if we can do a little bit of this as a chalk talk. So here's the overall picture we have, right? We want to think of our system as something that takes in inputs u, and then gives us behaviors, trajectories, whatever, x. So we want to be able to play in, some interesting input u. It's going to be a function from time into our input space. And then what we would like to have happen is that if we start from some initial state, x0, and we get some trajectory, we'd like it to be the case that if I started somewhere else, say y0, that as this thing played out over time with that exact same feed-forward input u, so not changing the u, not doing state feedback or output feedback, that this trajectory over time would converge, that I would just get asymptotically, for every specific feed-forward input I applied, just one behavior that comes out the other end. This is what seems to be happening. This is what's happening in Rex for a variety of Bueller clock feed-forward input parameters. Hypothesize this is what's happening in the cockroach as well. And so, really, when we think about feed-forward inputs yielding stable behaviors, what we end up with is that trajectories are forgetting their initial conditions. So if I think about, as time is going forward, if I think about the distance between points on one trajectory x and then another trajectory y, this distance is going to 0 over time. And just to get a little bit better handle on this mathematically, if this forgetting happens fast, so in particular if it happens at an exponential rate, then we're going to give it a special name. So if we have that this distance, xt, yt, if that's bounded, if it decays at an exponential rate, e to the minus ct times the initial distance, then we're going to call this system contractive. We're going to give it this special name. And this is something, I didn't make up this terminology or this theory. This comes from the literature. There's a really famous paper by Lohmiller and Slotin, and then Eduardo Sontag has done a lot of work on this as well, and it's a very old idea from physics. So there's really a very rich theory of when we can predict or when we can design a system to have this contractive property. So if we go back to just classical, smooth differential or difference equations, I can get this wonderful global property that all trajectories are moving toward one another. I'm getting one stable behavior out no matter what input I play in. And I can characterize that in terms of just local infinitesimal properties of my differential or difference equation. So the condition looks, formally something like this. I look at the maximum eigenvalue of the symmetric part of the Jacobian of my vector field in the case of differential equation, and then I want that, if I want my bound to be exponential in time with constant c, then I want that to be uniformly less than c no matter which point I evaluated in space. And then in the case of the discrete time system, I want to look at the maximum singular value of the Jacobian of that difference equation, and I want that to be uniformly bounded by this k if I want it to decrease exponentially at rate k in time. So this is a really, to me, a very striking mathematical observation because on the left, this global contractivity is this really strong property on the whole system's behavior. Your system is rather boring if it's contractive, boring in a potentially useful way, but does not exhibit super, interesting dynamics. All trajectories are converging toward one another. If there's an equilibrium, there's only one. If there's a limit cycle, there's only one. There's no chaos. There's nothing, super interesting happening. And that can emerge. And there's an implication in one direction, local contractivity, this infinitesimal thing is sufficient. Actually, there's kind of an if and only if, and if you allow me to be kind of funny about how I choose my coordinates or how I choose the distance metric that I'm going to use on the left-hand side, it's kind of a weak if and only if, so that's why I'm qualifying it a bit. But anyway, I think this is wonderful because, at design time, I don't know the range of behaviors I want my robot to do. What I do know are the infinitesimal kinematics. Right? I can compute the Jacobian of my, manipulator arm or something like that. And if it behaves in kind of a spring mass stampery kind of way, that's what these conditions on the right would amount to, then I can conclude that no matter what input I plug in, I'm going to get one and only one behavior out. We have a question?
Just about understanding. So
yeah.
The big garbage pile in the ocean is locally contractive, right? And then that doesn't imply that it's globally contractive, does it?
don't think that I understand the question. Let me see if I can understand the question.
Globally contractive if and only if locally contractive. So an example of something locally contractive is the garbage pile in the ocean, which if you're near it enough, you will get attracted to it. But that doesn't mean you can throw garbage anywhere and it'll always end up there. So
fair enough, great point. So what's kind of buried in what I've written here on the right-hand side, this local contractivity condition, is this needs to hold at every point in the state space or the region of state space that I'm interested in. This would not happen if I had, multiple equilibria, as you're saying. I can stand here or I can stand over here. Those are distinct, potential attractors or something like that. In that case, this local picture couldn't actually hold.
So that's exactly what I was going to ask.
Yep.
DF, but that term, lambda max square root, has to be less than C, the same C.
Everywhere. Uniformly at every point. Correct. So if you think about, if you just go, the linearization principle would tell us, let's look at the linear case and see what this tells us. In linear case, this doesn't tell us anything. This just tells us the exact same things that we know about conditions for linear stability. The thing about linear systems is that they are isometric. They're the same everywhere when you take their Jacobians. And so if they hold at the equilibrium, then they hold everywhere, and this is kind of trivial. The fact that this generalizes to nonlinear systems isn't so much surprising as it is kind of cool and potentially useful. Any other questions? Those are great questions. Yeah.
You have to have discontinuous vector fields depending on the topology, right? Because you're going to have equilibria, things like that, where this is going to vanish.
So you could conclude, if what I'm saying up here is correct, then you could conclude if you had a system with multiple stable equilibria that it could not be globally contractive.
But even unstable equilibria, I think.
Probably, yeah. Yeah, definitely. Even if you had multiple equilibria, then it can't be globally contractive because those 2 points don't converge to one another. For sure. So yeah, contractivity is an incredibly strong property. I would argue that it's kind of the property that we want to engineer into our systems because we want them to be insensitive to the exact voltages that we apply to them, and we want them to be insensitive to the terrains and the environments they interact with. So at some level, this is kind of the closed loop behavior we want. Whether or not this is the route to engineer that behavior, I think is an open question. I want to keep moving to get to kind of the punchline. So this is kind of a beautiful classical story I told you, but the problem is that the systems that everybody at this conference I think cares about are not classical, right? So in a mechanical system, subject to unilateral constraints, I'd have, configuration variable Q1, that's the height of the top mass, Q2, that's the height of the bottom mass, and then I'd have some unilateral constraint on the height of the bottom mass that says that it can never penetrate the ground. And so then the dynamics of the system will look something like this. If you'll forgive me for being, lumping terms and being a little bit stylized. I'm going to have forces that will depend on the positions, velocities, and possibly my external input that's just feed forward, so it's purely a function of time. And then I will have ground reaction forces for whatever contacts are presently active, and they kind of look like that. And then, so this is kind of the continuous time flow of the system, and then when limb impact occurs, velocity will update discontinuously according to some impact law, choose your favorite, plastic, elastic, whatever. Oops, that should be a minus. And this happens whenever a constraint becomes active. So that classical contractivity theory, although it has kind of nice analytical appeal, doesn't directly apply to the systems we're interested in. And so what I want to talk about for the remaining couple of minutes is our efforts to generalize this to this class of systems, and then try to generalize and then apply to this class of systems. Successful at generalizing, somewhat successful at applying. We'll see in a sec. So in order to make sense of this, we're going to have to agree on a notion of distance for these mechanical systems. This is something that I think is a super fun problem, kind of interesting. If I'd had a couple of more minutes, I would have done a think, pair, share kind of thing like I do in my lectures, because I think it's super informative. But imagine that I was just throwing a bouncy ball at the ground, right? So you know what's going to happen. Bouncy ball goes down. When it hits the ground, instantaneously, it's going to reverse direction. This happens at essentially the same time. So I'm going to denote this with like time just before impact, t minus, time just after impact, t plus. And in the phase space, the system, gets dropped from some height, follows a ballistic trajectory, and then instantaneously jumps over to this new initial condition, and then bounces up. If it was elastic, then I would have potentially lost some energy here. So if you ask the question, what is the difference between these two states? I'm at the same configuration, but I have opposite, well, at least opposing velocities that are opposite direction, possibly different magnitude. I'm going to give you just 1 second to think about it. You look at the picture on the top right, and it really looks like they're quite different. But then if you think about it from a dynamics kind of point of view, if I'm at a state at time, just before time t minus, and then immediately after time t, I'm at another state, they really shouldn't be very far apart. I really shouldn't regard them as different. So my answer to this question, I'm not saying it's the only, and I'm not saying it's the only useful, but in the context of contractivity, it's useful. My answer is that these are at zero distance, which is a little bit heretical because if you look in the top right picture, they really don't look like they're at zero distance, but I'm going to do some mathematical, hocus pocus, and I'm just going to declare them to be that way. And then we worked out the details in a paper from a few years ago about whether or not we actually, showing that we get an actual distance metric that obeys the mathematical laws that we need it to obey. So now that I have the right notion of distance in my pocket, I want to generalize this to hybrid systems, meaning piecewise defined dynamical systems that govern the kind of mechanical systems I'm interested in. And it would make sense, since I showed continuous time systems before and discrete time systems before, that if you want the hybrid system to be contractive, then you want it to be contractive in continuous time. So you want this sort of lambda max, maximum eigenvalue of symmetric part of Jacobian. I know that I'm running out of time, to be less than c. And then in discrete time, one might imagine that you would want the maximum singular value of the Jacobian of your discrete time thing to be bounded by k. But this second thing turns out to be wrong. And it's wrong because of the guard condition, the interaction with the ground and the geometry of the surface and your flow to get there. So this picture doesn't exactly explain it, but really what you need to do is you need to look at what's called a saltation matrix, something that takes into account not only the discrete reset that you're going to get from that map, and the first order effect of that, but also the difference in the vector field immediately after and the vector field immediately before, kind of properly stitched together through your reset map in the direction of your surface normal to your guard, this dg there. And then the condition that I want is that the singular values of this thing are, if I want stability, then I want this less than 1. I want these less than 0. And so the upshot, the funny thing is that if we only cared about dxr, then mechanical systems would have given us exactly the property we want, because the way things reset when they hit the ground is they lose energy, and so they project away dimensions. But then if we look at these funny augmented matrices that we get because we have a hybrid system, none of them are contractive. So that's the punchline. And if I'm lucky, I might have 1 minute for questions.
Questions?
So they're not contractive, or they're not contractive with your obvious coordinate system?
That's a great question. The coordinates that I've chosen are the ones that seem natural in the sense that I'm using like the energy as a metric to induce the metric, and those are the ones with respect to which, if I do my, let me pull up my pictures again. If I wanted to get contractivity of the continuous time dynamics of these, then energy would seem like the right metric, and each of these models would be contractive. But then my hands are then tied to use those metrics in order to look at the singular values of these funny linear matrices, and then that forces these to be expansive. And so what I don't know is whether I just need to look in the right coordinates, but at least the coordinates that seemed natural didn't give me the result I expected or hoped for.
Given your definition of globally attractive, it feels like if the only thing it's attracting to is a periodic orbit, it feels like it implies phase stability as well. In other words, the two trajectories need to converge and be in lockstep in phase. Isn't that too strong a kind of thing to attract to?
So this is a good point. I have two answers. One answer is that yes, when I'm talking about global contractivity in this sense, I'm letting the feed-forward input determine the phase. And so all trajectories are going to converge toward one another, and where they're converging to is going to move around in time as dictated by my input. So my input is going to clock the system, if you want. That's answer one. Answer two is that there are sort of partial or horizontal versions of this. You can quantify contractivity in some coordinates and not others, and so you could potentially, I haven't done it, but do a transverse kind of version of this where then you wouldn't require contraction in coordinates you don't want to, like phase.
I think we had Michael back there.
Just to follow up on what Manoj was saying, why contractivity instead of something like passivity or stability, something that's not as strong? Because I think contractivity is really, you said it yourself, is really strong.
That's a really great question, but to me, I guess, two answers again. First answer is, well, wouldn't it be nice? But okay, you're already on the same page on that. Second answer is, this is going to happen. Well, let me say this. I have these results for the classical case. I can look them up in textbooks and established papers. In the classical case, this is inevitable if we want to get the kinds of behaviors I think we want, which is that I'm going to have a closed loop system at the end of the day, after I've done all my careful design and engineering, that rejects perturbations, that I can modify my inputs slightly or parameters slightly, and it doesn't dramatically change the behavior of the closed loop system. And in that case, the classical theory says that, yeah, actually in the right coordinates, your system is going to have this contractivity property. That said, there are plenty of interesting, useful systems where the region over which these coordinates exist and are meaningful and are interesting is very, very small. So I don't think that this necessarily gives us like the total picture or answer. But the reason that I'm interested in it is because we can go from this local, infinitesimal, maybe kinematic or dynamic analysis of a system that I think is tractable because it's in linear land, and then potentially gain global conclusions.
Okay, I'm afraid we're going to have to wrap up. Let's thank Sam. Coffee break, 10 minutes. 10 minutes.